In this chapter, we talk about magnetic field lines. So first you notice the magnetic field lines of a bar magnet. So this is a bar magnet. And you can see that the magnetic field lines are coming out of the North Pole, as you can see here, and they are going into the South Pole. So they are entering the South Pole and they are coming out of the North Pole. Now this is a current carrying loop. So for a current carrying loop, it is also the case that it almost looks like a bar magnet. So you can see the direction of the magnetic field. So the magnetic field is going like this, in this direction. Notice the direction here also. And the magnetic field is going in the up direction like this, and it is entering back in like this, as you can see this. So this almost looks like a bar magnet. So saying that, bar magnet almost looks like a current carrying loop, we can use the formula for current carrying loop to calculate the magnetic field. So since the current carrying loop almost looks like a bar magnet, so this is approximately equal to a bar magnet. As you can see, the North Pole is upwards, the lines are going out of it, just like here. So just like here, the lines are going out. So this you can see as the top side of the coil, this is the bottom side of the coil, and the current is flowing in this direction. We have already drawn it here. So we want to use the formula for current carrying loop and approximate it to a bar magnet, and then find the magnetic field at say distance x. Now in the previous chapter we had talked about a current carrying loop. So we talked about a current carrying loop which had a radius of a, and we had to compute the magnetic distance or a magnetic field at a distance x. So this is the setup we had, and based on that we had this formula. Yeah, where a was the radius of the loop. This was radius of the loop. Now if x is really bigger than a, then you drop this term. So you drop this because this is very small in the denominator, so it does not make much impact. So if you drop it, this is what you get: mu naught I by 2 a square divided by x square to the power of 3 by 2. You simplify it, you get this result. That is mu naught I a square, this divided by 2, this divided by x cube. So this is the magnetic field at a distance x such that x is really bigger than a. Now we want to define magnetic moment of a loop, because we have this area A and we want to get rid of this area A. So we introduce a new terminology called magnetic moment of a loop. So this magnetic moment is nothing but a vector term. So this is the vector which represented by mu vector. This is the current flowing in the loop times a vector, and a vector is the normal vector perpendicular to the area of the loop. So this is the loop we talked about. This loop has radius a. So the area vector, the magnitude of the area vector is pi a square. But a vector by itself means normal to the area vector. So this is the a vector. You have the loop here, and the area vector is normal to this, the area of the loop, and the magnitude of this vector is pi a square, where a is the radius of the loop. So this gives you a magnetic moment. You plug magnetic moment into the formula here. So this is what you want to do. You want to take this magnetic moment and you want to somehow plug it in here. Now you already know that the area is pi a square. So what you do is you multiply and divide this by pi. So you multiply this by pi and you divide this by pi. Now this pi a square, this will become the magnitude of the area, and then you will have 2 pi in the denominator. So this becomes magnitude of the area, but now you multiply it by I, you get mu vector. So you take magnitude of the mu vector here, because we are talking about the magnitude of the area pi a square, and you get the magnetic field at distance x as mu naught over 2 pi times this magnitude of magnetic moment divided by x cube. So this is how we get for a circular loop, the magnetic field at a distance x, and for this circular loop, x was really bigger than the radius.